Now let's take a look at the plate bending theory. Now we talked about the axial deformation of 2D elements. Now you can just consider the plate as the 2D version of the beam element in one dimension. So the plate will bend in two directions. So how do we define a plate? We are saying that a plate bends if it carries load normal to its mid-surface. Now the plate bending theory ignores stretching or contraction through the plate's mid-surface. Remember that when we talked about the beam theory, we are saying that we have a neutral axis, and at the neutral axis there's no axial deformation. Now the plate, again, like the same thing at the mid-surface, which we can just think of it as the neutral axis of the beam, there is no axial deformation. Now the plates, we may define very different types of plates, but plates in structural mechanics is actually classified in two parts. The first thing is that we call them thin plates. So thin plates uses the Kirchhoff theory. So as the name implies, shear deformations are ignored. So a Kirchhoff plate is the 2D version of a Bernoulli-Euler beam. And we have also a thick plate. And thick plates uses the Reisner-Mindlin theory. And it's like the Timoshenko beam. And we have a first order transverse shear deformation is considered. Okay. Now let's see how we define a plate. So I'll say plates. So let's say that we have a member like this. It has a certain thickness. And this is the depth of the plate. We call it T. Let's say that this is the x-axis, and we have the y-axis here, and that will be the z-axis. So we have the material normals, so material normals in z direction. extending T/2 above and below. And by definition, we are saying that all the loadings must be in the transverse direction. So the mathematical idealization of a plate is, we just considered in the 2D member. This is the mid surface. So we are just taking the mid surface as T/2 from top and bottom and define our plate element. Now let's define the stresses and the relationship between the stresses and the plate forces. So for this purpose, again, I'm taking an infinitesimal element and let's exaggerate it. So that's the x direction. Let me draw it from the mid plane. Oh, oops, sorry. That's the middle. This distance is T/2 and T/2. That's the x-axis, local. That's the local y-axis. That will be the z-axis of the infinitesimal element. And this distance is dx. And this one is dy. Now let's show the stresses. So I can have a stress along in the x direction. Sorry, erase that, that's small and difficult to draw. I can have bending stresses in the x direction on the x face. So in linear variation. So these are stress x face applied in the x direction. And I can have the bending stresses in the y. So a linear variation in between. Stresses at the y face and in the y direction. So these are the axial strains, and we will have the shear strains in this way. So shear strain at the x face in the y direction. So I should have this same shear stresses in the opposite direction. Shear strain on the y face in the x direction. And we can also have the vertical shear stresses. And that would be the variation. Shear stress at the x face in the z direction. And let me show it this way. It's in the upward z direction, and that shows the variation. Shear stress on the y face along z direction. So if we use the Kirchhoff theory, Kirchhoff model, which is for the thin plates, we are ignoring the shear deformation along the depth of the member. So our stress vector will be composed of axial stress in x and y faces and directions and the shear stress. Okay, we are saying that these are negligible. Since our plate is thin. Now the Mindlin theory. Remember that we are using for the thick plates. Our stress vector have 5 components this time. 2 axial stress components and 3 shear stress components. Now these are the stresses. Let me write it here. And let's define the forces. So I'm just using the top view of the infinitesimal element. This distance is dx, that distance is dy, that's x direction, that's y direction. Now the moment due to this axial stress is this one, mxx, and the moment due to that axial stress is defined as, should put 2 arrows here, myy. And along, since it's along the infinitesimal element, I should just show it this way. Now we have the moment due to that shear stresses, that's also called the torsional moment, and I'm showing it this way. This is mxy multiplied by dy, and I have myx multiplied by dx. So for the Kirchhoff theory, our force vector will be composed of 3 moments, mxx, myy, and mxy. Now let's take a look at the shear forces. Now I have theta xz, so the shear force will be in the upward direction. I'll show it this way at that face. Vx times dy, and I will have Vy times dx. So for the Mindlin theory, our force vector will have 5 components, mxx, myy, mxy, and I have the shear force Vxz and V, YZ. So I should put Z here, I forgot to write them. And remember that these force components are defined for a unit width. Okay, so that again, let me repeat, they are not like the ones that we have in the beam elements. It's moment, but a moment defined per unit width of the element. And likewise, the shear forces are also defined per unit width. So let's put it as a note. So member forces, or let's call it element forces, not member. Element forces are defined for a unit width. So these are the definitions. Now let's relate the stresses with the forces. So force stress relationship so moment xx will be equal to, so I'm integrating from minus t over 2 to plus t over 2. And the moment of each stress is stress multiplied by the moment arm. Sigma xx multiplied by z integrated over the depth of the member will give me the mxx. So I can write the same thing for myy. That's equal to from minus t over 2 to plus t over 2 sigma yy multiplied by the moment arm z integrated over the whole depth of the member, and the torsional moment mxy will be equal to minus t over 2 to plus t over 2 tau xy times z times dz. So these are the moment stress relationships. We also have the shear forces. Vxz will be the integration of minus t over 2 to plus t over 2 tau xz times dz, and shear yz is equal to minus t over 2 to plus t over 2 tau yz times dz. And these are the force stress relationship. Now the next step would be determining the kinematic equations, which relates the member end displacement with the strains. Now let's take a look at the kinematic equations. I'll do it for the Kirchhoff theory and then also for the Mindlin theory. So kinematic, in other words, strain displacement relationship. And we are doing it for the Kirchhoff theory. Now, what we are assuming here is this: material normal to the original reference surface, remains straight and normal to the deformed surface. Deformed reference surface. Now for this, let me first draw the original surface. So let's say that this is our original mid surface. And let's say that that's the local x direction. We have the local y direction. And this is the local z direction. Now rotation in x. And this will be the rotation in y, or the derivatives of the members. So these are the positive directions with the right hand rule. Okay, now let's say that our element deformed in the z direction, and the new mid surface has a shape like that. So let's show some material axes here. They are all perpendicular initially to the original mid surface. Now here we are saying that normal to the original reference remains straight and normal to the deformed reference surface. So let's draw that. So here this should be normal. That's 90 degrees. That's 90 degrees. That's 90 degrees. Okay, so the bent member will look like that. And this is the deformed configuration. Now I will just take a look at this point. So it was here before and it moved in the upward direction by W amount. So originally this is the axis of the material, but it rotated as follows. So that's the angle of rotation, and this is our theta y. Now in my derivation, the counterclockwise rotations are positive. This is what I will assume, okay? That's the way I will drive it. So theta y here is clockwise. So minus theta y will be equal to, since the plane sections remain plane and normal to the reference frame, I can directly write that the slope of the mid surface of the deformed configuration should give me the rotation. So in other words, theta y must be equal to del of w with del x. So here we are saying that rotations are equal to the slope of the mid surface. and this negative sign is because we have a clockwise rotation. So I can just rewrite this equation as follows. Theta y is equal to minus del w over del x. Now if I write the same thing for the x direction, now with the right hand rule, the rotation in the x direction is counterclockwise. So I can write the same equation as follows. Theta x should be equal to del w over del y. Okay. Now let's draw this fiber in here, exaggerated way, deformed and undeformed configuration. So I have, that's the z-axis and w is the deformations along that axis. That's the x-axis and we have the u. So I'm just considering this fiber with a unit with an infinitesimal displacement. That distance is dx. This distance is t over 2 and again t over 2. Let's take a point at the mid-surface. Let's call it O and take another point P, and the distance is Z. Okay. Now this is the original configuration. Now let's draw the deformed configuration. So according to this figure, W is in the plus Z direction and we see a clockwise rotation. W in plus Z, theta y in clockwise. This is Z and W. This is X and U. So we see a translation. So point O was here. So let's say that it moved to this point. This is O prime. Point P was somewhere here. And let's say that it moved to this point, P prime. And let me draw this later on because so what we see, let's draw the deformed shape, a rotation and movement in the vertical direction. So this angle, they remain 90 degrees, no shear deformation, and point P moved here, that's P prime. Okay, and we said that this angle is theta y and this angle will be del w over del x, and we said that they are equal to each other. Now let's take a look at this. That's our translation of this point. This is u, and we know that the distance between these 2 points are equal to z. In that case, u can be written as equal to z times theta y. Okay. and this is the deformed configuration. Now, from deformed configuration, I get u as equal to z times theta y. Okay. Now, in the other direction, in the x direction, the right-hand rule gives us the counterclockwise direction, and when you draw the same figure in the counterclockwise direction, you will get v as equal to minus z times theta x, and that will be equal to, let's put this one into this equation, we have minus z times del w over del x, and this is equal to minus z times del w over del y. So this is the relationship between the axial deformation and the rotations. Now let's write the strains now. Now let's use the engineering strain definition. Now we know that epsilon xx, the axial strain in the x direction, is equal to del u over del x. So put this into that equation, then that will be equal to minus z times del square transverse displacement divided by del x square, which is equal to minus z times curvature xx. This is very similar to the beam theory. Now epsilon yy is equal to del v over del y, and that's equal to, again, minus z times del square w del y square, which gives me minus z times curvature yy. So this represents the curvatures. Now the shear strain is equal to del u over del y plus del v over del x, which is equal to minus 2 times z del square w del x del y, which is equal to minus 2z times curvature xy. And these are the strain displacement relationship for a thin plate element. Okay, now let's take a look at the kinematic equations for the thick plates. So we are using the Mindlin-Reisner theory for this. So the main difference here is it accounts for bending and shear deformations. So let's draw the same figure one more time. This is our plate. That's the mid surface. This is the original configuration. This is the x direction. the y direction, and this will be the z direction, and these are the positive direction if we use the right hand rule. Okay, so the derivatives of the transverse displacement will be in these directions. Now let's draw the deformed configuration. So let's say that we will have a deformation as follows. So I have a material axis here, another one here, and another one here. So these are originally 90 degrees, but as it deforms, they don't have to be 90 degrees because we have shear deformations now. So just to show that, let me first plot the 90 degrees. And let's say that that's the material axis here, that's the material axis. That's the material axis at this point, material axis, and let's say that this is the material axis. So that's the way we will see the deformations. And this is the deformed configuration. Now let's take a look at this material axis. So this distance is W. Now we know that this angle is del W over del X, okay? But we have some deviation from 90 degrees. That's that deviation. This is our shear strain, gamma xz, and then the rotation will be this one. That will be the theta y. Okay, so we can write the theta y as follows. Let me write it here. So theta y is a clockwise rotation. So I'm just saying that minus theta y is equal to the difference between del v over del x, del w over del x, minus the shear deformation, gamma xz. And here I'm just putting this minus sign because I'm taking counterclockwise rotations as positive. So from that equation I can just write theta y is equal to minus del v over del x plus shear strain xz. So in a similar manner, I can write the following. Theta x is equal to del w over del y plus shear strain yz. So as you see, we have the first order correction. In other words, a linear distortion due to the shear deformations. And once we have that, these are the rotation definitions. Then again, let's take this and exaggerate. This is Z and W. That's X and U. that's our fiber. Again, that's point O, that's point P. This distance is Z. That's T over 2. That's T over 2. Again, we do the same thing. W in plus Z, and we have a clockwise rotation. This distance is dx, by the way, and this is the original configuration. So let's draw the coordinate axis one more time. That is Z and W, and here I have X and U. Now drawing this is not that straightforward, so we have, let's start from the top. Let's say that it moved this way, and we have some angle change, so I will exaggerate and draw the angle change as follows. Let me redraw it one more time. So these angles should not be 90 degrees, okay? Let's see. I think I was able to draw the shear deformations. Now these corner angles are no longer 90 degrees. So we see distortion at this both edges, alright? Now this rotation is equal to del W over del X, and the rotation, this edge is equal to theta Y. So point O was here initially, so it moved to that point, O prime. So our P prime, let's say that it's here now. It was here before. This displacement is W, but we are interested in this displacement. And that one again I can write U is equal to Z times theta Y. And from this figure I can just write the following: U is equal to Z times rotation Y, and V is equal to minus Z times rotation X. Now I can define the engineering strains. Strain definition. So epsilon xx is equal to del U over del X, and that's equal to Z times del theta Y over del X. Epsilon yy is equal to del V over del Y, and that's equal to minus Z times del theta X over del Y. And finally, gamma xy will be equal to Z times del theta Y over del Y minus del theta X over del X. So we have also the additional out of plane shear terms. they are here. So let's write it down. Gamma xz is equal to theta y plus del v over del x, and gamma yz is equal to theta x minus del w over del y. Okay, so these are the strain displacement relationship. So the difference of this engineering strain definitions from the tin plate element is I was able to write that the rotations are equal to the first derivative of the transverse displacement. So I was able to represent the curvature in terms of the transverse displacements. But here, if you look at the rotations, now the rotations are no longer equal to the first derivative of the transverse displacement. We have the shear strains also. So that's why I can only show the strain in terms of rotations, not in terms of transverse displacements. And we have two additional strain terms, which they have the rotation and as well as the transverse displacement terms.